Assalamualaikum dear students. Welcome back to the Learn Daily Physics. And in the previous lectures we discovered a lot of things about plasma. We talked about Debye sphere, Debye potential, and we calculate the value for lambda d. So today we are going to talk about plasma frequency. What plasma frequency is, what frequency is. First we will discuss, but first I will tell you what frequency is, why when we use frequency, the term frequency. So let's talk about what is frequency and why we use frequency first, that you can have a better understanding about plasma frequency. So in plasma, or let's have a general look that when we talk about frequency, we know that frequency is reciprocal of the time period, and for a time period we have to cover some cycle. Frequency is of cyclic process which repeats itself. Okay, an oscillation, an harmonic motion, simple harmonic motion, or an harmonic motion, or any kind of oscillation or vibration. If a motion is in the same direction, we don't have any kind of frequency for that. For example, for a DC current, we don't have any frequency because DC current is like this. If you have 5 volt here and time here, that it will be in this. Or where we consider a sinusoidal wave, it will be like this. So it is covering some cycle. It's some cycle here. It will be at 2 pi, and in how much time it is covering that, it is equals to t, and t is equals to 1 over f, and f is equals to 1 over t. We have certain frequency. So for a plasma, we see what is frequency for the plasma. So we discussed that in plasma. Let's look that we have a plasma here, we have a positive ion here, and because of this positive ion, a negative ion was present here, an electron. We say an electron. Plasma is an ionized form of gas, and as it is an ionized form of gas, we will have a positive ion and a negative ion of that gas. So we see that we heat plasma is at high temperature, we get plasma. So plasma, these electron get thermal energy, gets some thermal energy here and absorbs it, and from absorbing that thermal energy, it gets excited. Okay, it wants to move. Now it have some thermal energy. It want to dislocalize, it want to be delocalized from here, it want to move from this way. Okay, we say that it moves in this way. When it go here, from this point to this, from this point to this, okay, so what happens? It consumes all of its thermal energy, but now the magnitude of the Coulomb interaction between this charge and this particle is more than its thermal energy. We have a comparison between Coulomb energy, let's say Coulomb force, and thermal force. You can say that the thermal energy, Coulomb energy and thermal energy, it's more convenient to say like this. So when the thermal energy is greater than Coulomb energy, or the Coulomb potential, you say, this will move away from the charge. Okay, this electron will move away from the charge. It want to break the barrier from this ion. Okay, so when this energy is less, it will come more closer to this ion. Okay, how much it will come? The displacement is lambda D. It will form, there will be a lot of ions here, and all of these ions will form a sphere around it, and we know that the distance between them is lambda d. We already discussed it. So when this Coulomb E and the thermal energy is equal, then our system is at equilibrium. It is not moving either in this way or this way. Okay, so when this, it utilize all of its thermal energy from moving here to here, this point to this point, this was its equilibrium point, and again Coulomb energy is now greater than thermal energy, and it will move backward. It will come to its equilibrium position, but due to inertia, because iron have some mass, and inertia is intrinsic property that it is inborn in a mass, that when we have mass we have inertia. Okay, we have mass, we have its inertia. So because of inertia, it won't stop here, it will go here, just like a simple harmonic motion. You consider a case of pendulum. It moves here, then it comes here, it won't stop here, it goes here, and again it starts oscillation. Just like that, in the plasma, it won't stop here, it will shoot here, and then again it will come back. Okay, so in this case it will oscillate in this direction. Okay, it will oscillate in this direction. So I think you understand the basic terminology now. So this was the when the electron moves away, these are the all lines are written for that you understand. In this manner, plasma will start oscillate with certain frequency, which is called, when the thing oscillate, it have some frequency. I already told you about that what frequency is, how frequency is related to an oscillation, that when a system oscillate, it have some frequency, and that frequency is called plasma frequency. So let's say that we have a charge E, accumulation of charge E, and from that accumulated charge E, we have an electric field. Electric field, you know that electric field is the gradient. Field is gradient of its potential, negative gradient of its potential. So this is representing partial by partial, or you can say, so this is del dot phi is equals to E, and del dot E is equals to rho over epsilon naught, Gauss's law. So n naught here is the electron density at equilibrium. When the ions are at equilibrium, this is that the density of that electron or that charge or that ion, you can say, and n1 is the variation in that charge density. Okay, n1 is the variation in that charge density. So let's start with a calculation. Our theoretical work is over now, and now we are going toward our calculation. So for our calculation, we say that the total number of electron is Ne plus N naught plus N1. How this term form? You will say that where does it come from? So don't be panic, I will tell you. So as you look at, you have to consider that you have a system, and in that system you have a small change. That just like you say that we have theta, and we have a small change, theta change, this was theta, and we have a small change from here to here, and this is d theta. So overall change will be theta plus d theta. You have a length, you have covered distance, some l distance, then you cover some dl distance, length element, so total will be l plus dl. So in this case we have n naught original plus n1 the variational, the changed one. Okay, so ne will be equals to n naught plus n1. You better understand what I told you. So this Ne will be equals to original value plus change. I dropped it. So now we write the Gauss's law. What is Gauss's law? That rho is equals to, better write it from this pen, del dot E is equals to, it's so it is so fade, del dot E is equals to rho over epsilon naught. So now we have to calculate what rho is, what is the density for this plasma. So as we know, the density of a plasma, rho is equals to number of electron into charge of electron plus number of ion into charge of ion. Okay, so this one is negative E into Ne is equals to N naught plus N1, N naught plus N1, and rho equals to plus Ni is equals to Ni, and this is E. Okay, so the first thing we do, we will multiply this term here. And as I told you earlier in our previous lectures, that these ions are relatively rest. So positive ions are relatively rest from electrons. Because why they are at relative rest? Because when you talk about an ion, when you talk about ion, you say that ion is bigger than, larger in size than electron. Okay, so because of that, electron will move here to here, while positive ion will cover a distance in that time from this point to this point. So comparatively, okay, in comparison, relative velocity is, they don't have any relation here. There is a lot of difference between their velocities, so we will say that they are relatively at rest. Their relative velocity is zero. Okay, so we say that ions are at rest. From that ions are at rest, so we can say that they are at rest. We can say ion Ni equals to N naught, because when the system is at rest, their equilibrium, we say that it's an equilibrium state. So N1 is, Ni is equals to N naught. So multiply this value, rho equals to E N naught plus minus E N1 plus N1 N naught E. Okay, so this N naught will be cancelled out from this one, and now we will get that our value, that rho equals to minus E N1 over, this rho will be here, this term, and from that del dot E will be equals to minus E N1 over epsilon naught, minus E N1 over epsilon naught. So now we know that the value for F is equals to Q E, and here F will be equals to Ma, Q will be equals to minus E and E here, and we divide this M from, it is in multiply here, so A will be equals to minus E over M, this term from here comes here, and to E. Okay, A is equals to minus E over M E. Okay, so we will write this A as dV by dt equals to minus E over M into epsilon naught. Okay, epsilon naught, this is not epsilon naught, this is electric field E. So this is equation number 1. We write another equation here and we name it as equation number 1. that del dot we already described an equation, and this equation was that del dot E is equals to rho over epsilon naught. We put the value of E is equals to, we have this value, this, we put the value of E here. Let's say we put our value here, and from this equation we get del E is equals to minus del phi, so del phi minus and equals to minus E n 1 over epsilon naught. So it will make a term del square of phi, a Poisson equation, and this minus will be cancelled out from this minus, and we will get del square of phi equals to E n 1 over epsilon naught. We will write it as equation number 1 and this as equation number 2. Okay, so now we are going, you have to put pressure on your brain. You have to tell me what equation of continuity is. In thermodynamics, what was the equation of continuity? Can recall? So I will tell you. So the equation of continuity is that partial rho by partial t plus del dot j is equals to 0. This was our equation of continuity. So if we say that ni and ne was the, I told you that these are the electron densities. Ni is the n naught is the electron density at equilibrium, and n1 is the change in that density. So in the case of, in the terms of electron density, we will write it as Ne, it is the volume charge density by partial t, and plus del dot n. Now j is equals to nev. The v is the drag velocity here, so del dot j, no, now j was not here, we are writing nev for j and it's equal to 0. Okay, j is equals to this term, ne is equals to j over v and all that. So we know that ne equals to n naught plus n1. Put this value here, so partial n into partial n naught ne will be equals to partial nv will be equals to partial n naught over partial, I'm taking the partial by partial t of this equation, it will equals to partial by partial t plus partial n1 over partial t. Okay, so from this we can say that this term goes to 0 because this is at equilibrium, and equilibrium, it is not changing with respect to time. When it's not changing with respect to time, it will be 0. So this term goes to 0, and here from this we can conclude that partial ne over partial t is equals to partial n1 over partial t. Okay, putting this value in our above equation, so putting this value and this one also, this equation number a and this equation number b in our third equation, so partial n1 over partial t plus del dot ne will be equals to n naught plus n1 into v. Okay, so as we say that in our equilibrium state, the number of particles in equilibrium states are so much than their variation. Just like that, you have 1000 rupees here, or you have 1000 particles, and 10 particle left or 1 particle left, you say there is a small change, 1 particle left, the overall will be 1000. We will say that it's nearly 1000, or in when we talk about particles or densities, we have hundreds of thousands of these values. So small change doesn't matter that much. So n naught, so this n naught plus n1 will be nearly equal to n naught, because if this variation occurs, there is not overall change in n naught will remain same. We say that we have a condition here, we apply a certain assumption here. So from that we can say that partial n1 by partial t plus del dot n naught v is equals to 0. Here it was 0, okay, equals to 0. Okay, so now we take the derivative of this equation. We again take the partial by partial t of this equation. So when we take the partial by partial n1 by partial t partial square by partial t square plus del dot n naught partial v by partial t equals to 0. Okay, when we take the again differentiate this, it will form an equation like this. And now we say that partial n1 partial square of n1 partial t square plus del dot n naught, now we have a value of this partial v by partial t we already calculated here. This partial v by partial t is equals to minus e over m epsilon naught. Okay, equals to minus e over n epsilon naught. This was e or positive e, this was a negative e here. N naught partial v by partial t is equals to e over m. So let me check that the value I put it here is right. So yeah, but we are neglecting the negative sign of electron here to make our term. Yes, we are not taking our negative term here. Partial by partial t e over m. Yes, in this value we took this value as e is equals to negative gradient, and this term we've modified this term as E is equals to del of phi, negative del of phi, and from that dv is equals to dt, dv by dt is equals to minus this minus will cancel out from this value, putting the value of E here, so it will be equals to E over m del of phi. Okay, E over m del of phi. So we will write this equation as equation number 2, and we will put the value of dv by dt from this equation. Okay, so now we have del of phi here and del of phi here. So our lecture is completed, going to complete now. So E over m, we have this value E over m del phi, E over m del phi here. So this E is not here now. So when this is the del square n1 over del t square plus this will be n naught and del square of phi into e over m. This was e over m. Okay, solving this equation. Yes, so we already described also value for this del square phi e n1 over epsilon naught, which was equation number 1. So from equation number 1 we are going to put the value of del square of phi. That will be equal to partial, it is equal to 0, it is equal to 0, del square of n1 by partial square of n1 by partial t square plus e over m n naught into del square is equals to E. So when we put the value of this del square phi here, this value of partial v by partial t, then we put the value of del square phi, we will get an equation, ultimate equation like this. And this is a second order differential equation with respect to t of n1. And here this is a constant term, we are having a constant term here, just like dB length we are having some constant term here, and this constant term is known as omega p square, omega p square, and it is equals to omega p square is equals to E square n naught over m epsilon naught, E square n naught over epsilon naught and m epsilon naught. Okay, m epsilon naught, and from this omega p will be equal to under root E square n naught over m epsilon naught. So as you look here in your equation, this is equation number, this is a second differential order equation, and we will solve this differential equation. If you've studied ordinary differential equation, then you can solve this equation easily. Okay, so it will equals to partial square by partial t square of n1 plus E square n naught over m epsilon naught, E square n naught over m epsilon naught, n1 equals to 0. This will be d square plus, this will equals to d square n1 plus omega p square n1 equals to 0. So d square plus omega p square n1 will be equal to 0. So d square plus omega p square equals to 0. D will be equals to plus minus iota omega p. So this was the characteristic equation. We call this a characteristic equation, and we've studied in our ordinary differential equation. This is a topic, or this is the course of ordinary differential equation. If you want to learn everything about it, you already know about it, but if you forgot everything, then you have to review the ordinary differential equation. So this is a characteristic equation, and from this characteristic equation you form an auxiliary equation. Every characteristic equation has an auxiliary equation, and the auxiliary equation for this characteristic equation is, we are going to find n1 will equal to n naught e power minus iota omega p over t. Okay, this will be the auxiliary equation for this characteristic equation, and from this we can calculate n1. Okay, it shows that, let's write it here, that it shows that density variation changes with respect to time. Changes with time. That density changes with time. From previous equation you can also see that density is changing with time, and from this equation also you can see that n1 is changing with time. So this is in a denominator and we have a minus sign here, so overall value will be bigger. Okay, it will be an exponential rise. So omega p is equals to, we can write this omega p again. So omega p will be equal to e square n naught over m epsilon naught, and we will omega p will be equal to e square over m epsilon naught, and this is a constant term, and n naught can vary for a one plasma to another plasma. This n naught can vary, but this is a constant term for all of the plasma. Electron, charge of electron, mass of electron, and epsilon naught, the permittivity of free space. This is the permittivity of free space, epsilon naught. It is a constant term, and this whole term is nearly equal to 50. Okay, is nearly equal to 50 and n naught. Okay, so from this we can say that the frequency is directly proportional. An overall estimate we can make that frequency is directly proportional to n naught, and from this equation, above equation, this one and this one, we can say that the omega p will be greater for dense plasma. As the density of plasma increases, the value of n naught will increase, and as the value of n naught, the number of electrons at equilibrium state will increase, then the value of this omega p will also increase. Okay, so you understand the plasma frequency, and now we find the relation between the plasma frequency and the n naught, and we also know that when omega p increases, n naught increases, and n naught increases, omega p increases. Okay, so our today's lecture is over now. Thank you very much for your time. Subscribe to Learn Daily Physics and visit our website www.learndailyphysics. If you want any helping material, helping books, or helping notes for this, and you can contact me from there. And you can also contact me, you have any question, you can also contact me on my email, learndailyphysics@gmail.com. So thank you very much for your time. Assalamu alaikum.